By now, you should be getting pretty used to the structure of these chapters. We just got done learning how to do significance tests on P problems, and now we're going to switch over and look at significance tests for mu problems. So we're doing HOHA style problems to make a verdict about a population mean, mu. And there are going to be three conditions for problems with mu, just like there were three conditions for everything else. And see if you can pause me and remember what those three conditions are in a mean problem. Two of those conditions are not going to change from what they were before. So we're going to have the random sample condition, and we're going to have our good old 10% condition, ensuring that our trials are approximately independent, which allows us to calculate our standard deviation. And our third condition was called the central limit theorem. And there were actually a couple options for how we could check this third condition. The central limit theorem itself was that your sample size is at least 30. So we had that option. We also, instead of using the central limit theorem, could just declare that our population is normal. And then at the end of last chapter, we actually learned a third way we could check this condition, and that was to graph our sample data. If we graph our sample data and it's not strongly skewed and there are no apparent outliers, that basically tells us that, you know what, it's plausible that the population could be normal after all. And then we're allowed to keep on going. The t-distribution is good at handling situations like that where you have like a little bit of a gray area. T-distribution will still work well. So those are our conditions that we need to check. Pretty much what you guys saw last chapter when we did confidence intervals. There's going to be a test statistic that we calculate for mean problems, just like there was for the P problems we did last section. And if you guys remember, when we do mean problems with mu, we end up bringing in the t distribution. So when you're doing one of these problems, we would like to do sigma over square root n for our standard deviation. That was the formula for standard deviation of x bars sampling distribution. But that uses real sigma, and we don't actually know sigma most of the time, because that's the population standard deviation. So what we do is we sub in that s, and when you sub in s for sigma, that's when you need to use the t distribution. So this guy right here with this s plugged in is your standard error rather than the standard deviation of your sample mean. So just like last video, we ended up doing a test statistic z equals, and that guy started out statistic minus parameter. We went p hat minus p. Well, now we're going x bar minus mu, and then we divide by our standard deviation formula. The t distribution has n minus 1 degrees of freedom, which is basically just a measure of your sample size, and we're going to talk a little more about that t distribution on our next slide. So, the t distribution, we introduced it last chapter. And even in this chapter, we're not going to go super in-depth in terms of where it came from and stuff. That's something you'll see more of if you take a more advanced stats class in college later on down the line. But we talked about how a t distribution in general has like shorter heights to it, so it doesn't reach up as high as a normal curve, so it's a little bit shorter, and the area on the edges in the tails is higher than that of the normal curve. The reason for that is that S has more variability to it, so you end up getting results that are further away from the center more frequently. But as the graph progresses, so if you look at this picture right here, the red graph at the right here along my cursor, the red graph has 2 degrees of freedom, meaning that the sample size for that guy is 3. When you have a really small sample size, the tails of the graph get pretty large because there's a lot of fluctuation when your sample size is that small. Then it put another example right here in teal with 9 degrees of freedom, that being a sample size of 10. And you can see what happens is the shape of the t distribution actually changes a little bit depending on the degrees of freedom. When you increase degrees of freedom or you decrease You increase degrees of freedom, you increase sample size, you decrease the variability between samples. So you're not going to get as much area or crazy results in those tails as you do when the sample size is really small. And then if you look in purple right here, if you keep on increasing your sample size, you end up getting the standard normal curve, which is right here in purple. So when sample size goes up in the t-distribution, you actually get closer and closer and closer to looking at the actual normal distribution. I have here your formula sheets, and it's on the page with the t-distribution, which we talked about. We've seen this page before. But if you look at the degrees of freedom along the side right here, the degrees of freedom keep on going up, and they get to 20, and then it keeps on going, and then they start jumping to 100 and 1,000 degrees of freedom. And finally, at the very bottom here, they actually do a thing for infinite degrees of freedom. As those numbers get really high, look at the 1,000, look at the infinite level right here. The numbers for the cutoffs here for 90% and 95%, those, actually all the numbers, but those two in particular are the ones I mentioned last chapter that I had memorized. Those are actually going to be your standard normal cutoff values that we use, 1.645, 1.96. So as your sample size increases, the t distribution actually morphs into a normal distribution. The tails get smaller, and then it gets a little bit taller as well because you don't have as much of those crazy fluctuation cases that you do when your sample size is small. So there's a few points right here on this slide with regards to just things to know about the t-distribution. I've mentioned several of these already. The spread of the t-distribution is greater. That's why there's more area in the tails. Saying the same thing right here. And then as your degrees of freedom increase, the density curve gets closer and closer to what the actual normal distribution is going to look like. All right, so let's look at our example problem right here and talk about how you run a 4-step on a mean problem. So these two girls really like to eat sub sandwiches, and then they're advertised as 6-inch subs, and they look to see if they're actually being cheated at the restaurants and they're deliberately cutting, or maybe not deliberately, but they're cutting the bread too small so you don't get as much as you actually paid for. So what they did is over the course of a few months, they randomly selected 24 different subs and measured the bread to see exactly how much they were getting. These right here are the results for these 24 trials. So anytime you're dealing with a variable that is quantitative or numeric in AP Stats, we aren't going to look at the individual numbers and try to do something with those. Instead, what we actually test is the average or the mean of all of those data points. So when we run a test on a series of numbers, we're not saying, oh, you can't have numbers below a certain amount, like, oh, you can't have a 4.5 or something like that. All we are testing is whether the mean is what they say it's going to be. So there are going to be days where they cut the bread a little bit short, but there's also going to be days where they cut it a little long. Over all of those different days, we want to see if the average value is what they say it should be. So we're going to go ahead, and because it's a quantitative problem, we are going to set up a significance test for our mean, mu. And they'll say on average right here, which is a signal to you that we are testing mu. So the first thing we're going to do is set up our hypotheses here. We're going to have HO and HA. In this problem, we're going in just assuming that nothing fishy is going on, status quo, and that would be that the subs are actually 6 inches like they're supposed to be on average. So the HO, null hypothesis, is going to be that the mean is 6, like it's supposed to be. And these girls, let's see if it gives in the problem an indication what they think. So they think that the subs might actually be shorter than advertised. So the girls are looking for evidence that actually the mean is going to be less than 6. We're going to define our variable mu. It is going to be the true average length of a sub at this location. Presumably they did this all at one shop right here. I kind of skimmed the wording here. Yeah, it's at their favorite restaurants. So that's going to be our state step. And in order to really make sure we have it all, I'm also going to include our significance level. Remember to do that before you actually do stuff with your data. They tell us that they want to use a significance level of 0.10 in this problem. So that is going to be our significance level. The next thing we're going to do is check our conditions. And when we check those conditions, I'm going to start with the nice easy ones here. First off, it's a random sample of 24 subs, so that's good. 24 is less than 10% of all subs at this location. So that's also cool. And then these two girls, if they only could have taken 6 extra data points right here, we would be great. We would just say n is greater than or equal to 30, and we would move on with our lives. But unfortunately, they only did get 24 data points right here. They fell short of the 30. Does not say the population is normal. So we're going to graph our sample data. So we got to pull up our calculator here and go to the good old stat menu that we're used to. I'm going to go ahead and type in this data, and then I'm going to look at a box and whisker plot. I'll come back with that momentarily. All right, so I saved you guys the trouble of watching me punch buttons here, and I came up with my little box and whisker plot. I went over how to do that in a previous video. Go stat edit, type in data, go second y equals, turn on stat plot, etc., etc. You need to do a zoom 9 to see this picture. And then if you hit the trace button right here, you can figure out what the little boundaries are that you need. So I went ahead and transferred over that graph. After you draw the graph, you need to look at it and say, could this data set have come from a distribution for the population that was actually normal, like we want it to be? And when you look at this, there is perhaps a little skew to the right. Both this section right here and this whisker are a bit longer. So there's a tiny bit of skew maybe, but there's no outliers, which is really good. And it's not horrible skew. So instead of saying, oh, it's relatively symmetric, because maybe it's symmetric, maybe it's actually a little bit skewed, I'm just going to say I'm going to say nothing yet. I'm going to say no strong skew or outliers. No strong skew / outliers. So the t distribution is appropriate. It's plausible the population is normal, and if the population is normal, we can still move on and use our good friend, the t distribution. So those are going to be our conditions here. The next thing we're going to do, there is going to be like a calculator shortcut like there always is, but we're doing it the longer way, or the real way, this time without the shortcuts. Why? Well, it's important that you guys understand how it works, and it builds character too, and it'll be fun. So it's going to be so great. Over on the side right here, I reminded you guys what the test statistic formula looks like. With P problems, you didn't have to do it this way. You could just go straight to normal CDF with numbers from the problem. But I said this at the time, you can't actually do that on these kinds of problems here. So we're going to do it the test statistic way because it's the only way we can. Now this formula starts out with an X bar. I do not yet know what X bar is. I have to find the average of these numbers. I do know what the mean is. The mean in the HO, that's going to be 6. So I can at least plug that in. Don't know what S is. I could find that using my little standard deviation formula, perhaps, divided by the square roots of 24. So these are the parts I know right now. These are the parts I don't. So it's a little bit like, okay, because I'm going to make you use the calculator anyway, because I'm not finding the mean of all those numbers by hand. That's not going to happen. So what we're going to do, the data is already in our calculator. I'm going to go stats, calc, and when you have a list in your calculator, you can find the mean and standard deviation and stuff by doing one variable stats. My data is an L1, no frequency list. It's not a chapter 6 probability style question. And if I hit calculate, my X bar is about 5.68, and you want the S here, not the sigma. S is 0.657. So 5.68, 0.657. And I'm going to write that down before I forget it here. 5.68 and 0.657, I think I just said. Let me check it. 5.68, 0.657. Wonderful. And then what I'm going to do is I'm actually going to calculate my little test statistic right here. I will go ahead and button push on this, do the top and bottom separately, then divide and get your t. All right, so I typed that in. I got t equals negative 2.386. After you get your test statistic, that's going to help you get your p-value. So what we need to do now is look at the t-distribution. So I'm going to draw a little picture for that. It's still centered at 0, just like a normal distribution is. I got a negative 2.386, and our HA was a less than for our alternative. So I want the area less than negative 2.386. All of those values here would be more extreme than the one that I got. When I do this, I'm going to use the TCDF option. And for the TCDF option, one of the things it's going to ask me for is my degrees of freedom here. Let me see if I remember. I don't remember what order the commands go in. So I'm going to choose second distributions. I'm going to go TCDF. My lower is small number, that's fine. My upper was negative 2.386. In my degrees of freedom, I had 24 subs. That's 23 degrees of freedom. And if you type it in, you probably should use a negative sign to get that correct. I got 0.0128. So 0.0128 is going to be our p-value. So when I did TCDF, our lower was negative big number. My upper, and I'm running out of room right here, negative 2.386. And make sure on these problems you do include the degrees of freedom somewhere in your answer. The degrees of freedom were going to be 23. We got this p-value. Once you know the p-value, it's nice and easy. It's just conclusion time, and that should be second nature to you guys now. So go ahead and write a little conclusion based on this, and I'll write it down myself. So what I would want to say for this is, since our p-val is 0.0128, which is totally less than 0.10, which is our alpha, we reject our null hypothesis. The evidence is strong enough. That test statistic was rare enough. There is convincing evidence. The true mean sub-length is less than 6 inches. So there's convincing evidence that HA is in fact true. Please make sure when you do these problems, I said this last chapter, but in conclusions with mean problems, kids frequently forget to mention the word mean or average. If I don't see average in your answer, you will lose credit for it. You have to talk about average because it's mu we're testing. If you just say there's convincing evidence the subs are less than 6 inches or something like that, that's not true. There are also subs that are greater than 6. It's the mean that's definitely less than 6. So based on our conclusion that we just got done with here, could we have made a type 1 error or a type 2 error, and then explain what this would mean in context? Please pause me, think about that, and answer that bottom part yourself. I'm going to pause myself and come back with an answer here. Okay, so we rejected HO. That means we could have made the type of error you make when you reject HO. It could be a type 1 error. Type 2 involves failing to reject. So a type 1 error in this context would be finding convincing evidence that the subs are too short on average, when in reality, they're not too short. So I have a basic explanation of that written down below. Go ahead and make sure you have something similar on your own papers. We're going to do one more example problem in this next video, and I'll probably take pieces of it and just kind of put them up there to save a little bit of time here. Go ahead and look over this problem right here, and I want to talk about a few things. On the side, you'll see a little bit of computer output. So this is off of a program called Fathom. And whenever you have computer output, there's going to be a key that tells you what everything means. So basically, the order of this right here, the mean is 29.4, count is your sample size of 50, you have the standard deviation third, and you have the standard error fourth. And what's actually going on in this problem is we're looking at the cube size. I don't know if when you guys were younger, you played a game called Don't Break the Ice. I totally did as a kid, where you just like take a little hammer and knock the little cubes out and stuff. If those cubes are off by too much, it's going to ruin the game because then they're not going to fit like they're supposed to in the little box. So there's going to be a machine, and they actually test and do quality control on these little blocks to make sure that they're the right size. Before we get into the actual significance test here, we're going to talk really fast about two interpretations. Interpreting the standard deviation, which we've totally done before, and interpreting the standard error, which I'm not sure I've talked about in a video yet. So this will be a chance for me to address how to do the second one here. But go ahead and try to write down an interpretation for the standard deviation of these cubes yourself. Okay, I've got my standard deviation first, and this one you guys should already know how to do. Remember that standard deviation is your typical distance from the mean. It talks about a randomly selected data point, how far that typically is from your overall average. So if your standard deviation is about 0.09, that means that a randomly selected cube will typically be off by about 0.09 millimeters from the mean of 29.4. So some might be a little bit too high, some might be a little bit too small, but if you average all of those distances, it'll be approximately 0.09 millimeters for the average distance to that mean. The standard error is something I have not formally made you guys interpret, so I'm going to do that right now, but I'll write it up there first for you. All right, so this part is new. The standard error first came up in this class after we learned about sampling distributions. So remember that the sampling distribution for x bar's graph, was approximately normal if conditions were met, and it's centered, that was a really bad straight line, but it centers at the true mean mu. We don't actually know the true mean in this problem, so when I wrote my little answer right here, I didn't mention a value for it. 29.5 is what we think it might be, or we're hoping it might be, but they don't tell us the true mean. This is our sample mean right here. But what the standard error does for us when we calculate it, that's going to tell us the standard deviation of this graph, but we sub in S in place of sigma. So the standard error tells us the typical distance of values of x bar. We get different x bar values. We could get a sample mean that's too small or slightly too big or way too big. It's talking about how far those different x bar guys are from the true mean. So that's what's going on when we talk about standard error, your typical distance of x bar to mu at the center of the graph. To calculate this bottom number right here, what they did is they took their sample standard deviation S, which was this guy right here, and they divided it by square root of 50, because the sample size is 50. So if you take that 0.09 number, divide by square root 50, you'll get this number right here. So that's how you would interpret a standard error. So that was a little sidebar, but let's go ahead and talk about the actual significance test. I will help you establish the setup here, and then you should try this yourself. This time, we're going to use the calculator shortcut, so I'll have to show you where that is. So the first thing I want you to do is write down your hypotheses, and it would be good to pause me and try to write those down yourself, because I'm just going to talk about them right now, but it's always good to practice these. In this problem, they want the mean to be 29.5. And when they're making these cubes, it would be an issue if the cube was too small, because then it's just going to like plop through the board right there. It's not going to hold in place. And if it's too big, it won't fit in the first place where it's supposed to. So either direction is an issue, meaning that this is a two-tailed test, two-sided test. It's going to be a not equal to alternative. Mu is going to be the true mean length of cubes. And I believe this was in millimeters. Yeah, it is. And they wanted us to use the significance level of 0.05. We're eventually going to use the calculator commands, but I'm going to write up the conditions myself. They're not going to be painful to check this time. The calculator command for this section is going to be in the tests menu. You're going to want to do a t-test. Last time was t-interval in chapter 8. T-test is our option. So go ahead and write that down. It's calculator commands number 2, t-test. And see if you can pause me and play around with it, even though you haven't seen me do it yet, and see if you can figure out the answer. I'll talk about it in just a sec, so pause me now. Try it yourself. Okay, so let me go ahead and close this out. I have the answer written up there, but I want to comment on a few things here. When you go over to tests and you choose your t-test, number 2, there are 2 tabs, just like there were last chapter. Data is what we would have used if we were doing the last problem, where they gave us a list of numbers. This time, they didn't give us the raw data. They instead gave us just summary statistics. The summary statistics were in the little computer output on the previous page, this stuff over here. Now, when you're deciding what to use there, it was a little confusing, actually. So they give you the mu from HO is just 29.5. That's easy. Sample mean is cool. The S, if you're confused which of these to pick, this bottom guy is after you already divide by square root n. It's a little confusing that they gave you both, the S, because the third line right here, this standard deviation is S. This is S over square root n. Calculators wanted S if you did it this way. So you take that 0.09 number, you take your sample size of 50, and it was a not equal to alternative. If you hit calculate, it'll give you all this nice information. What you need to report to get full credit, the name of the test, t-test. You need to give the test statistic, which is that negative 1.209 number, and the p-value, which is the 0.2322. P-value, always a decimal, always a probability. I started reading X bar there. All that other stuff at the bottom, you don't need it. You can put it if you want to, but I probably wouldn't. So your p-value is about 0.23. What does that mean for us? Well, obviously we failed to reject and all that good stuff. You guys are probably pretty good at your conclusions by now. They got a sample mean of 29.48. They were testing the different cubes. Their average was 29.48. They wanted to see if that was different enough from 29.5 that they would be pretty sure the machine isn't working right. But that number was just too close. The probability of that or more extreme happening was about a 23%, too high for them to shut down production, fix the machine. It's a big to-do. So they would fail to reject the idea that the machine isn't working well enough. So they would just keep on keeping on, and they would not reject the null hypothesis.